Chapter 18, we're talking about some of the thermal properties of matter. We're going to introduce new state parameters. We're going to now be talking about pressure, volume, and temperature. We'll be talking about mainly a gas because it's easiest to kind of conceptually think about. And we'll be talking about what's going on a molecular level for a substance, and so how these molecular interactions are going to affect the properties of a substance. By that I mean the phase, whether it's a solid, liquid, or gas. So kind of hitting this point down here. We'll be relating the temperature and pressure to how much kinetic energy a gas molecule is going to have, and we'll extend what we know about heat capacities to talk about heat capacities for a gas and motion of its molecules. Some fun questions to kind of think about is, we have a hot frying pan. How do the speed of the molecules compare directly above the frying pan to the ones in the rest of the kitchen? Obviously these are going to be hotter, so what's happening is they're going to be moving a little bit faster. And then how do the atoms of a gas determine its pressure and temperature? So what we'll be doing is, I'm using the word atoms a lot. We're going to be talking about the microscopic properties of matter and how how temperature and pressure are going to affect the macroscopic or the large bodies. One new concept, one new physical principle that I need to introduce that we skipped when we skipped chapter 12 is this idea of pressure. No, not pure pressure, but pressure in terms of physics. We've always considered our forces to be applied to an object and say, okay, this object is now going to move. We've never really considered the fact that this object actually is a three-dimensional object and it's got some surface area to it. If we consider a box that has the wind blowing on it, so it's got the force of the wind applied over that entire surface area, we can now write how much pressure an object has, which is related to the force divided by the surface area. Force is going to have units of newtons. Area is going to have units of meters squared. So this unit of Newton meters squared is also going to be called a Pascal, abbreviated as such. If we consider, say, a box like this filled with some type of gas, that gas is going to be moving. It's got some kinetic energy associated with it. I'll talk more about this in a little bit. And that gas is going to be bouncing off of the sides of this box. It's going to be applying a force divided by a surface area. So there's going to be some pressure on the sides of this box. Same thing is true for the atmosphere, where we have air molecules that are moving and they're bouncing into every surface. So we know that we're going to also have some atmospheric pressure, which is actually going to be equal to 1.013 times 10 to the 5th pascals. Occasionally you'll see pressure written in terms of atmosphere, where we say, okay, 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. So atmosphere could also be a unit of pressure that you'll see on occasion. So if we want to talk about an object that is going to have a state, is it going to be a solid? Is it going to be a liquid? Or is it going to be a gas? I need to talk about some quantities that are going to be called state variables because they're going to determine the state of a substance. So these parameters you're already kind of familiar with a little bit are going to be pressure, volume, and temperature. Therefore, these are called state variables. It turns out that we can relate all three of these guys, the pressure, the volume, and the temperature, using this equation of state. From the equation of state, we can get a very important equation, put a star next to that, which is the ideal gas law. It's going to essentially describe how an ideal gas is going to behave, and we'll always talk about ideal gases in this particular class. It's going to relate the pressure multiplied by the volume must be equal to this little n right here, which is going to be the number of moles of a substance, which is related to essentially the quantity of the substance. You may remember from your chemistry class. Going to have this value r, which is essentially a constant. It's going to be 8.314 joules per mole degree Kelvin. And then the temperature, which is going to have to be in Kelvin, volume must be in cubic meters, we're working in the SI system, and pressure must be in pascals. If you want to use different units, you can find a value of R that will correspond to liters and atmospheres. Now what this is really saying is if we take an object and we increase the temperature, then this is going to be a constant, this will be a constant, and therefore the pressure multiplied by the volume must go up. Maybe one of them will remain constant, and the other one will go up. Maybe one will remain constant and the other will go up. But the pressure times the volume must correspondingly go up if you change the temperature. Same thing if you play games with the volume or the pressure, the temperature must also correspondingly change. We can relate the number of moles to essentially the mass of the object through the molecular weight, which is going to be essentially the mass per mole. I'll work a sample problem using this in the work problem set. Now we can use the ideal gas law to think about compressing gas in an automobile cylinder. Essentially you're going to have this cylinder and you're going to have an air-fuel mixture. It's going to have a certain number of moles of gas in there. I've drawn essentially 5 moles, and then a little bit later the cylinder is going to be compressed just before it gets ignited. So now I've drawn my cylinder, the volume has gone down, I still only have 5 moles of my air-fuel mixture in there. So I can say, let's take a look at this ideal gas law and relate the pressure and volume to the number of moles, to a constant, and the temperature. Now if I divide both sides of this guy by temperature, I'm going to see that pressure times volume divided by temperature is going to be equal to the number of moles multiplied by R, which is essentially a constant. So what I can do is, if I say that this is part 1 and this is part 2 of a compression stroke, that I can go ahead and I can say that the pressure at 1 multiplied by the volume at 1 divided by the temperature at 1 must be equal to the pressure at 2 multiplied by the volume at 2 divided by the temperature at 2. And if I know essentially what some of these guys are, say initial pressure, initial volume, and initial temperature, and I know a final volume and a final temperature, then I can go ahead and I can solve for the temperature at the end of the compression stroke, as they do in example 18.2. So let's talk for a little bit about this ideal gas law. The pressure multiplied by the volume is equal to the number of moles multiplied by some constant and the temperature. Let's just kind of picture a box right here, and in this box we have 3 gas molecules, and these gas molecules are moving around. They have some temperature, they have some kinetic energy associated with them. Since the volume of the box is fixed, if I go ahead and I dump more and more and more energy into this box, it's going to go into the kinetic energy of the particles, so they're going to be moving a little bit faster. What that means is they're moving a little bit faster, they're bouncing off of the walls here. That's going to provide this thing called pressure. So if I increase the temperature, I'm essentially increasing the kinetic energy of the gas, therefore I'm increasing the pressure. Similarly, if I were to increase the number of moles, if I say double the number of particles in this gas right here, increase the density, I should also correspondingly increase my pressure. And similarly, if I were to reduce my volume. Now, this ideal gas law ignores the fact that these molecules have size. It ignores the fact that they bump into each other on occasion. But for everything we do in this class, this is going to be the equation to use. There's an equation in your book, van der Waals equation, that's a little bit more realistic. It says gas molecules have volume, it reduces the volume they can move in, and they're going to exert forces, gravitational forces on each other, reducing the pressure, but really stick with the ideal gas law for this class. A neat way to look at the ideal gas law is to look at these things called PV diagrams, which we'll be using quite a bit in the next couple of chapters. Essentially, we're saying that the pressure times the volume is going to be the number of moles multiplied by that constant R multiplied by the temperature. Now, if I just pick one temperature and say the temperature is going to be constant of the system, and I play around with the pressure times the volume, the pressure times the volume is going to be equal to this thing right over here, which I've said now is going to be a constant. So I can say the pressure times the volume at one point must be equal to the pressure times the volume at a second point over here. So if I look for a given temperature, it's going to be this. This is going to be one temperature, this is going to be another temperature, this is going to be another temperature, and this will be another temperature. The pressure times the volume right here, so P1, V1, must be equal to the pressure times the volume over here, and you can kind of see there's going to be an inverse relationship. Essentially, what we're saying is if we have a balloon and we squeeze one end of it, if we decrease the volume over here, the volume must increase over here because I've applied a pressure over here. These blue lines, these lines of constant temperature, are actually going to have a special name. It's going to be called isotherms. And all that really is a line of constant temperature on a pressure versus volume diagram. Pressure over here, volume over here. So let's take a second to go back and talk about matter now on the molecular level. So let's take a look at solids, liquids, and gases. On a molecular level, if we think about molecules and how they interact with each other, it's actually going to depend on their separation distance R, or more or less how closely packed in molecules are to each other. Solids are going to have very small separation distance. There's going to be a lot of potential energy that is holding a solid together. So they're essentially fixed in place. Liquids, their separation distance is a little bit larger, so there's a lot more freedom of movement between these guys. A solid is going to have a definite volume and shape. A liquid is going to have a definite volume. It's not compressible. However, the shape is fairly malleable. Gases, you can essentially think of them as molecules that are free to move, and they're not attached to any other molecules. So they have almost no separation distance, and they keep on going in the direction that they're going until they bounce into another atom or into a wall, as I was showing you on the next page. You can look at more complicated versions of the force and potential energy, but really for this class you're not going to need a more complicated view. So here I am, I'm talking about molecules that are bouncing off of walls and everything like that, but you say, well, when you talked about that ideal gas equation, PV is equal to N times R times T, turns out that before I was talking about the number of moles of an object. Here I'm talking about molecules, so let's go ahead and relate these two. Now, I'm not big on chemistry and moles and all that good stuff, but this is the SI definition of a mole. Really, I've been able to my entire life get away by thinking of the number of moles as simply being a quantity. We can relate how many molecules there are to 1 mole of a substance using Avogadro's number, which is this number right here. It says, okay, if you have so many moles of a substance, you can convert it to molecules by multiplying by this number. The molar mass is simply going to be the mass of 1 mole, so we can write the molar mass in terms of the number of molecules multiplied by the mass of a single molecule. So we're going to now start talking about pressure, volume, and temperature and how that's related to the speed of the gas molecules that are inside of a container. So essentially kinetic energy related to molecular energy. So we're going to have this kinetic molecular model. Now this model is well, fairly simplistic, but the physics gets quite complicated otherwise. So just a couple of basic assumptions or caveats is we're going to have a huge container with a very large number of perfectly identical molecules. Not always true, but good enough for government work. Molecules are going to behave like point particles, and they're going to be in constant motion and undergo perfectly elastic collisions, so energy is going to be conserved. And lastly, the container walls are perfectly rigid and do not move. Again, all of these are not necessarily true in the real world, however, it greatly simplifies the physics involved. So what we can now do is we can take a look at molecules that are colliding with the wall. They're essentially got a molecule right here. It's got some kinetic energy. It's going to bounce back off of the wall. It's going to have some kinetic energy afterwards, and I said on the last slide that we're going to say that these kinetic energies are the same. We know that it's impacting the wall. It's got some velocity, so it's going to exert some force on the wall, and actually it's going to be a force divided by area. So what we can do is we can use energy conservation to write the velocity of the particle in terms of the pressure on the wall. And if you're really interested in the derivation, you can certainly look at the book. What we can come up with is we can come up with an expression that's going to relate the velocity of the particles essentially equal to the temperature of the gas. So what we do is we say that there's going to be some RMS speed of the particles. That's going to be a root mean square speed of the particles, and that's going to be related to the 3 times that constant R that keeps popping up, the temperature of the gas, as well as the molar weight of the gas, that big capital M. Now this root mean squared right here, essentially what that's saying is it's kind of like an average. The gas is not necessarily going to be a constant temperature from one side of the particle to the other, so this is you can think of it as roughly an average temperature or an average velocity of the gas molecules as they transverse the cylinder. If you want to see the difference between the average and the root mean square, take a look at example 18.7. Really the root mean square puts higher weighting on the particles that are moving faster, which are going to really give us more pressure here.